Now consider a current carrying conductive solution that has a homogeneous composition and a constant cross-sectional area. For clear visualization, let's draw the uh, plates of the electrodes. So this is first plate and the second one. So the area between these two electrodes is shown as red color. So this area A is the cross-sectional area that is present between the surface of these two electrodes, and it is considered that the solution is homogeneous, having the composition same at any point within these two electrodes. As the composition of the solution is constant at every point, so the current density will be constant at every point in the conductor. As the current density is constant, and this one is the electrical conductance, that is the constant value. So for constant value of current density at every point, the field strength E will be constant at every point in the solution that is present between the two electrodes. So for this condition, we have only 2 points, that is x1 and x2. So this integral equation is derived from this differential equation is given here. So we can rewrite the equation 5 as equation 9, which is showing the del phi, showing the electrical flux or the electric potential difference between the two electrodes. In terms of current, we can write this equation, which is labeled as equation number 10. In terms of current, the current density is the current per unit area. That is the change in position, change in flux with respect to position. Let's consider the distance between these two electrodes is equal to power x2 minus x1 is equal to L, where L is the length of the conductive solution. So we get the equation 11, which is the current per unit area that is dependent on the electrical potential difference between these two electrodes. So we can write the electrical potential difference as the absolute value of electrical potential difference is equal to these factors. So the conductivity or the electrical conductance can be defined in terms of the electrical resistivity. So in terms of resistivity, the electrical potential difference is expressed here. This electrical potential difference is often called the voltage, having a unit volt. So here resistance of the solution is defined as electrical potential difference over current, or the flux is, or the potential electrical potential difference is equal to current into resistance. So equation 12 is redefined as question 13, which is showing the relation of resistivity with resistance, or the electrical resistance of the solution. The unit of electrical resistance is ohm, whereas which is expressed as 1 volt over 1 ampere. So that is actually equal to 1 kilogram meter square per second per coulomb. Which is given here. The unit of resistance, that is ohm, which is expressed in terms of kilogram meter square per second per coulomb square. The unit of resistivity is ohm centimeter or ohm meter. As explained above, that the electrical conductance or the conductivity is the inverse of the resistivity. So the unit of the electrical conductance is per ohm per centimeter. The per ohm is usually written as mho, which is the inverse of ohm, and the correct SI unit of the conductivity is Siemens, that is S. So this S is only for conductance, that is reciprocal of resistance. That is expressed as per ohm or per mho. So for the unit of conductivity or the electrical conductance, the unit is Siemens per centimeter. Here few points must be noted, as the conductivity is depending on the composition of conductive solution, and that is independent of the magnitude of current density or the dimensions of solution. Whereas the resistance depends on the dimensions of the cell as well as the composition or type of material that is conductive. As the electrical conductance is the inverse of the electrical resistivity, so these two parameters have similar correspondence, but that is inverse. As the kappa or the electrical conductance is independent of the magnitude of current density, so it will also the independent of applied potential, that is the electric field, hence that is independent of the magnitude of the current density. So such solutions obey the Ohm's law, which give the plot of current density versus applied electric field a straight line. So the solution of electrolyte obey the Ohm's law.